Hello physicists! Today we're going to be developing three kinematic equations which will be very useful in solving almost all linear motion problems. To start up, we're going to begin with a little warm-up activity. Now these notes, I'll tell you now, are already annotated. I'm just going to do a quick walkthrough. As we're going through, I would encourage you to pause periodically. I'll be going quickly so you can kind of read what's on the screen, digest it, and then I'll highlight the key points in my narrative. So in this warm-up activity, you've got a billiard ball that's rolling across a table in the positive x direction, hits the edge of the table at a perpendicular angle, and bounces back in the negative x direction, traveling at a different speed. We want to know where is the greatest magnitude of acceleration for this billiard ball. Recall that we're looking at a velocity versus time graph. So if you want to pause and think about this, when you're ready you can hit play and keep going. So hopefully you've thought about this a little bit. Notice that we're looking for the slope on a velocity versus time graph to tell us the acceleration. Acceleration, of course, is change in v over t. Well, the greatest change in velocity is going to be where the slope is the steepest, and so, of course, c is going to be the best answer here. So moving right along, you'll recall that in an earlier lesson we said the area under a curve tells us a lot of information. Particularly in a velocity versus time graph, the area underneath that line will give us the displacement of the area during that time interval. So for a nice level line, it's easy enough to find the area under a rectangle. The height times the width ends up giving us the same value as the average velocity times time. And that's true because the velocity in this case is a constant 30, it's not changing. If we have a slope graph where the velocity value is changing, we could essentially do the same thing, find the average velocity, and multiply that by the time. In this example, you can see we have a sloped graph. Triangle has the area of 1/2 base times height. Well, if we think of 1/2 times the height, that's really saying the average of the maximum height at 40 and the final height at 0, 1/2 times 40 plus 0 is 20. Which would be our average over this time interval. Multiply that by our time, and we're going to get our total displacement. And so this will give us a clue as to how we can algebraically solve for these. Some key bits of information. We're dealing with the initial velocity and the final velocity, and then something with the time interval here. So this is a relationship you want to tuck in the back of your mind. You'll see it again when we develop our equations more formally. If we look at a trapezoid, we still have a slope that it follows the same triangular pattern, except for there was no motion apparently in the first section before this purple portion of the graph. And so the purple section itself is a trapezoid, and we can use the 1/2 base times the sum of the two heights to solve for that area. Another way of looking at this, instead of finding the area of that entire trapezoid, is to break this into two familiar shapes. We have a rectangle, box 1, and we have the triangle on top of box 2. This sets the stage for what will become one of our main kinematic equations. The overall displacement, where we have x is the final position, x naught or x0 is the initial position, so this is our displacement, our change in position, is equal to v naught, the initial velocity, times time, and that's the total time of our travel, plus 1/2 times the difference in our velocity, v minus v naught over t times the time squared. Now this is a lot. We'll derive this again more formally, but if we kind of look at key points here, the object was starting at some initial velocity v naught, ends at a final velocity v, the time interval is t, and it goes across. And so really, the overall displacement should be the area of this first box, which is just the initial velocity times time, plus 1/2 times this difference. This height is going to be v minus v naught times the time that it takes to get there. I would encourage you to pause for a minute and just kind of think about this and see how the terms on the graph might be related to an equation. This is actually not the final version of the equation. I'll show you that in a moment. So this slide just kind of cleans up our efforts here to break our trapezoid into two shapes, recognizing that we have the triangle and the rectangle. And when we add the sum of the two components together, we do end up getting the same total area for our displacement. So either graphical approach which however you want to break up your shapes would work fine. If you wanted to, you can break this up into a combination of rectangles and triangles, smaller right triangles with rectangles underneath. That gives you more work, but mathematically it works out to the same answer. I want to quickly remind you of some formal definitions. So our velocity is the change in position, or the displacement, divided by the change in time. Typically, our initial time is 0. If you start a stopwatch, it starts at 0 seconds. And so delta t is really equal to just the final time on your interval. Now that's not the case if you're looking at a journey and you're looking at a segment in the middle of that journey. The clock's already been running for a while, then you have an area of interest, and then the clock continues afterwards. So delta t doesn't have to be 0, but typically we say it starts at 0 and you have some interval from there. Acceleration is our change in velocity over time. So the first kinematic equation is actually very straightforward to derive from our definition of acceleration. Change in velocity is the final velocity minus the initial velocity. The change in time is the final time minus the initial time. Again, if the initial time is 0, we can simplify this to t, and then multiply that, so at is equal to v minus v naught. Now we typically rearrange this to make an equation where the final velocity is equal to v naught plus at. This is your first kinematic equation. It's worth noting that on your AP equation sheet, they do put a little x subscript here, and this just means that this is the velocity in the x direction, the final velocity in the x direction. This is the initial velocity in the x direction, and this is the initial acceleration, or the acceleration for the entire trip in the x direction times time. This becomes more significant when you're dealing with two-dimensional motion because you need to separate what's happening horizontally versus what's happening vertically. At this stage in the game, we're only dealing with one dimension. So if you don't put the x subscripts in, that's fine. I just wanted you to be able to recognize this equation as the equation that is on your AP. It's probably worth jotting this down in your notebook now to use as a reference. You typically don't need to do these kind of derivations on the AP exam. I do think it's helpful to know where they come from because you will do other derivations, typically more involved than just developing your kinematic equation. So I think having an understanding of how these fit together and kind of a puzzle to make a set of equations that can be used in almost every situation is helpful. But highlighting what's in red and writing this down is a good reference point for it. This is just a quick practice problem that you can use as a reference. A strategy that I think is really helpful, especially as you're starting out problem solving. When you read through the problem, I would identify what variable each number is on your first read through. So we have a deer running at 10 meters per second. I would pause and say meters per second has to be a velocity. The deer is running at 10 meters per second and then slows to 2 meters per second. That means that the 10 must be the initial velocity and the 2 is going to be the final velocity. They're not always listed in initial and final order, so read carefully for the context. I might say that an object was traveling at a certain speed and then accelerates, so it could be getting faster. You could also see something where an object stopped after moving at a velocity of something else, in which case the stop would be the final and something else would be the initial. So read carefully for context. The units are a big clue. Seconds is time, so that's what we know. We know that's an easy one to identify. And acceleration is what we're looking for, so I would label that as the unknown. Sometimes you might want to make a list and just say, the list of all the variables you know. If you're fine just labeling it on the top of the problem, that's also sufficient. Now you've only got one equation to work off of, so this should be an easy one to follow. We know Vx, we know Vx naught, we know we're looking for Ax, and we know time. So there's only one unknown. We have an equation with everything else known. It's easy to kind of plug and chug. If we're solving for the acceleration, I prefer to algebraically solve for whatever variable I'm looking for first, and then put the numbers in. So I've got my raw equation. I'm going to rearrange by bringing the v naught term over and then dividing by time to get a, dropping the numbers, and I get an answer. Many students prefer to put in numbers first and then rearrange and just solve. That's valid. I think it's useful to practice doing the algebra with your variables as well, because you will see problems where there are no numbers, you're just doing the algebra with the letters. So whichever way you're comfortable with at this point, I would say it's good to practice that, but down the road our goal is to be able to do this exclusively with just variables, especially for the AP exam. Once you solve for your final answer, And I'll tell you up front that I don't always remember to put my units in, but if you do the algebra that you did with the numbers, as we did here, and do the same operations on your units, if you get the unit that makes sense for the quantity you're trying to measure, that's a great check that you've done to work correctly. For instance, I have a velocity of 10 meters per second, a velocity of 2 meters per second, so those are both in meters per second. We're going to pretend that we don't know the unit on acceleration, okay? And then we know time was 5 seconds. Well, when I bring the 2 over, those are both in meters per second, so subtracting units, I end up with the same unit still. That's equal to A times seconds. When I then divide the 5 over, I would get meters per second, and meters per second squared is the unit for acceleration. So the units check out. I have a high confidence that I've done that problem correctly. Our second kinematic equation comes from the definition of velocity, and I apologize, I had to edit the slide here. I realized I made an error as I started to read this out. The average velocity is the change in this position over time, or the displacement over time. If you have an average, you're really adding the initial and the final values together and dividing by 2. Now, for an object with no acceleration, it's easy to say v is equal to delta x over t, but because we are now accelerating, we have to consider the average velocity over that interval. T naught's going to be 0, so that term goes away, and we end up with x minus x naught over t on the right-hand side. The average velocity, the bar symbol above the variable indicates that you're dealing with an average. So that would be the final velocity plus the initial velocity divided by 2. This is my average velocity. This is the definition. If I multiply the TF, that T has to get distributed to the whole left side. And now recall that we just solved our first kinematic equation to say that V final is equal to V naught plus AT. If we substitute that in for V here, and I flip them around just for convenience of drawing this out, I end up getting 2 V naught terms and an AT term. So the 2 V naught terms become 2 V naught times that T, plus the AT times T is T squared. That whole thing's over 1/2. The 2 and the half cancel out, so we get a term with V naught T. The 1/2 on AT stays, that's 1/2 AT squared. And this is our final version of the second equation, x equals x naught plus x naught y, so x naught t plus 1/2 AT squared. If you want to pause and just read through this problem and try and solve using the second equation, I identified the variables and I kind of worked through. If you want to work through this on your own and see if you end up with the same final answer, that would be encouraged at this time. Our third kinematic equation is actually my favorite of the 3. So we have our first kinematic equation that we solve for. We're going to rearrange this to solve for the variable t. We'll then substitute this into our second kinematic equation anywhere that there's a time. We do that substitution. There's a little bit of algebra we have to work out, but if you follow along, you should see that a lot of stuff cancels out, and we end up with this elegant v final squared equals v initial squared plus 2a times the change in x. This is our third kinematic equation. And again, AT uses the subscript, so there's little x subscripts to indicate we're only talking about the x direction here. Notice that because we substituted for time canceled out in our final equation. We call this the time-independent equation. So whenever you run into a situation where time is not given and it's not being asked for, that's a good clue that you probably want to use time-independent. Here's one final practice problem. This one's a little bit forced, so really if you look on the left-hand side, you could solve this using your second kinematic equation. However, I wanted to show you that there's almost always, multiple ways to solve a problem. So although time is given here, if we wanted to, we could have used our first kinematic equation to solve for the final velocity, and then pretend that that final velocity was one of our knowns. We could use our time-independent equation to get the same displacement as we get when we use the second equation. There's almost always one way that's going to be more efficient. So in this case, the time-independent equation wasn't required, but I just want to show that it is an option, and this is what it would look like if you solve it through. So here's a summary slide with our 3 equations in the AP format. I apologize, this was a little rushed. I'm working on a demo version right now of Kinematic, and so I've got a limit of 15 minutes, which I'm quickly approaching. But I appreciate you hanging in there. I think we've given you enough to be dangerous. Please take the rest of this time today to work through the suggested practice problems, and I'll also post the raw slides so you can go through a slightly cleaner version. Thanks for watching.